Let's get started. Let's go. 9.3. So at 9.1, what do we do? 9.1, we talked about the basics of a significant testing, right? Basic of a significant testing. And then in 9.2, we actually did, okay, so how are we going to do a significance test on the proportion of a population, right? Population proportion. Now we're going to do the same thing, but we're going to do with a population mean, right? So we're going to do tests about population mean. So let's do some review. So population proportion, what do? How do I do the test? So I'm going to do plan, oops, state, plan, do, conclude, right? So what am I going to do? I'm going to state what I'm going to do, right? What kind of population proportion am I testing? So I'm going to state by putting the ho and the ha, stating what the alpha level is. Right? That's what I do in the state part. The plan part, what do I do? Yeah, check conditions. What conditions do I need to check?
Random.
Random sample is 1. What else? Okay, less than 10%. And then the large counts, right? And PSV greater than 10, n times 1 minus PSV greater than 10, right? Okay, so that's what we're going to do on the plan. And the do, we're actually going to do it. What does doing mean? What are we accomplishing here in the do part? What are we trying to find? You're trying to find the p-value, right? You're trying to find the p-value. We're going to try to find the p-value, and then we're going to do what with the p-value? Down here, to conclude, what are we going to do? Compare it to the alpha, right? If the p-value is less than alpha, what happens? Graded. P-value is less than alpha. This is a good thing for us, which means that we're going to reject the ho, and we're going to have convincing evidence for the ha. Right? Okay, that's what we want to do, right? Because if you remember correctly, the ho is what we're trying to disprove. This is what we're trying to disprove. This is what we think that is correct, right? So if we have a p-value that is less than alpha, we're going to reject the stuff that we thought was wrong. And we're going to actually say that what we thought was correct all along was correct. Okay? The p-value is greater than alpha. Then what happens? We failed to reject. We never accept the ho. We failed to reject the ho. There is not convincing evidence for the ha. Okay? So that's what we did in a nutshell. Okay? What we're going to do today is population mean. Guess what? This is going to be the same. This is going to be pretty similar. This is going to be the same. Okay? Calculating the p-value is going to be a little different. Okay? So keep that in mind and let's go ahead. Okay, so we have carrying out a significance test for you. We're on page 585. When we did the confidence intervals, okay, we checked for 3 conditions when we were doing the confidence interval for the mean. What were they? Same thing, right? Random sample, less than 10%, large count, right? What was a large count? Less or greater than 30, right? If you're greater than 30, we're going to accept everything, right? And what allows us to do that? The central limit theorem, right? The central limit theorem says if your n is greater than 30, your sample distribution from the population is going to be normal, right? So be normal. That's what the central limit theorem said. So if n is greater than 30, we're fine. If n is less than 30, what do we have to do? check. You're looking for no skewedness, no outliers, right? Okay. What would you expect the conditions for a significance testing? They're the same. Exactly the same. Because if you look at the population proportion, doing the proportion, the confidence interval conditions and the conditions for significant testing were exactly the same, correct? Same thing. So when we're testing for the mean, the bottom of page 585 gives you the conditions in green. So go ahead and read that. And it should bring you back to what we've been talking about. Okay, any questions on the green box? Shouldn't be. Same stuff we did before. Flip the page. Better batteries. Problem. Here are the lifetimes and hours of the 15 deluxe AAA batteries from the company's Simple Random Sample. Check the conditions for performing the significance test are met. So, the random sample, it says it's a random sample, right? Yeah, simple random sample, so we're good there. Is it less than 10%? I hope so. I hope you are making a more than 150 or more than 150 batteries, right? Now you got a problem there. And then the large counts. Does it satisfy the large counts? It's less than 30, right? It's less than 30. So you have to actually make the notion or say. So on the test, if I give you this question, okay, you have to state that it is less than 30. Therefore, you have to look at the distribution and you have to at least say that there are no outliers and it's roughly symmetrical. Better if you actually do the dot plot, right? Include the dot plot or the stem and leaf plot or whatever, right? Some sort of plot, histogram, something that shows me that it is actually roughly symmetrical and there's no outliers, okay? So that's what you would check. And you do that, and then lo and behold, yes, there are no strong outliers or no skewness. So standardized test statistic and the p-value. So in the proportion, how do we do the proportion? We had what? P hat minus actual P over what was it? Square root of this was our Z star, correct? This was our test statistic. Okay. So when we're doing the mean, it's going to be actually the same. X bar, I think, right? Use X bar and mu. So X bar minus mu over. This is the standard deviation, right? This is standard deviation. The problem is when you are doing, and we've had this before, right? This is the population standard deviation, right? The population standard deviation of the population, but we do not know this, right? And that forced us to use what? The t-distribution, right? So we're doing the same thing here. We're going to actually use the standard deviation of the sample, and we're going to use not a z, but you're going to use the t-distribution to find this. Okay, you can use the t-distribution to find this, and then you're going to use your t-distribution sheet at the end, right? The sheet T, that was what? table, where's the t dash? Oh, t dash 3. We're going to use the t dash 3 to find what the p-value is. Okay, so the rest is the same as we did the proportion, right? So when we're doing the proportion, remember we said that we went like this, and so this was the p, and this was the p hat, and we were looking for this, and we said this guy here was going to be our p-value, right? It was one-sided, right? It was two-sided, use both tails, right? It's going to be the same thing here. And instead of p, now we're going to use u, and we're going to use x bar, and instead of a normal distribution, we're going to use the t distribution, right? Because we're going to know the n, which gives us what? The degrees of freedom in the t distribution, right? So you have to know the degrees of freedom, right? Okay, so let's go to, we did that one. Okay, flip the page to 588. T distribution is described by a symmetric single-peaked bell-shaped density curve. Any T distribution is completely specified by its degrees of freedom and performing inference about a population mean based on a random sample of size n when the population standard deviation sigma is unknown. Use a T distribution with degree of freedom n minus 1. Okay. One more thing. Well, we talked about the T distribution already. We already talked about this. So I'm going to say this one more time. If I had, this is the normal distribution, right? The black is normal. The T distribution is going to be a distribution where it's slightly depressed. So you're going to push down here. So it's going to come like this. Where you're going to have fatter tails. The tails are going to be fatter because they're a little higher than the normal. The peaks are going to be a little low. Okay. As the degree of freedom gets larger, your T distribution is going to actually become more and more peaked. And it's going to actually go closer and closer to becoming a normal distribution. Okay. So if I want to compare a distribution or T distribution with a degree of freedom of 4 versus 40, right? So if this was 4, 40 is going to be closer to a normal distribution like this, like that. Dang it. Right? Okay. So just know the difference of the shapes there. Okay. All right. So let's go ahead and see if we can do an example and see if we understand this. Let's go ahead and do the example on 589. Suppose you want to perform a test of O is mu is equal to 5 versus ha mu is equal to not 5. Uh-oh. What's going on in the back of your head? This is a what? It's two-sided, right? Because it is the O was mu is equal to 5. I is equal to, oh, where mu is not equal to 5. This is a double-sided thing, right? It's not greater than or less than. It is not equal to, right? And we're using alpha of 0.01, 0.01. Random sample size n is equal to 37. Yields a u is equal to 4.81 and the standard distribution of that was, a standard deviation of that was 0.365. Okay. So what do we need to find? So this is the state part, right? The state, this is what we're doing. Do we check all that stuff, or did they tell you that we don't have to check that stuff? Oh, it says the tests are met. Okay, we're good. A, explain why this sample gives evidence. So why does this give evidence to this? Because it's not 5, right? Obviously, it's not 5. 4.81 is not 5. So B, calculate the standardized test statistic. So the statistic itself is going to be 4.81 minus 5 over the standard deviation 0.365 square root of 37, right? With a degree of freedom of 37 minus 1, 36, right? Okay. And if you look that up in the back of your table, you're going to end up with negative 0.317. Negative 3.17. So if I do this, I get negative 3.17. Okay, and the p-value, right? So I check the p-value, what do I get? So if you look at the back of the book, there is between 30 and 40. We do not actually have a degree of freedom of 36. So when in doubt, when you're in between two numbers, you're always going to choose the lower number, right? So you use n equals 30. So you're going to use a 30 degree of freedom. And if you do that, you find not an exact number. So this is important. You don't know exactly what the number is, right? Because it's between, there's not a number called 3.17, but you do know it is in between 0.0025 and 0.001. Okay, so you don't know exactly what the p-value is. So what is the p-value? Since it's between 0.001 and 0.0025, actually you have to multiply this by 2, correct? Because it's a two-sided thing, right? There was a not equal to. So it's going to actually, your p-value is going to be between this guy and that. I multiply this by 2, I get that. I multiply by this 2, I get that, right? So now I can compare that with the alpha, which is larger. So which is smaller or larger? What p-value is what compared to alpha? Smaller, right? Since the p-value is smaller than alpha, that's a good thing for us, right? We reject the whole. We have convincing evidence for the half, right? Okay, so we're good with that. Okay. Okay, all right, we're good with that. Good. And obviously, on the technology corner, it tells you how to do this using your handy dandy calculator. Okay, you're gonna go to stats. Oh, this is just okay. This is calculating the p-values from the distribution, right? Okay. All right. So it's a t cumulative distribution. So you're going to go from the t distribution, you're going to set the negative 100 to whatever it is. And I should see on their side. This is something else. Never mind. This is not the same example, is it? No, something else. Okay, right. So you can use a TCDF. There's no way you can do the t cumulative distribution function. Use that. All right, we're good. We are done for the first section.